Hey everyone, so this is the second video around logs and exponents, and here we're going to dive into log laws and just trying to deal with understanding the log laws. Most of them are on your formula sheet, so it's just a matter of knowing what to do when. We're also going to take a look at equations and applications of logs. We did exponential applications in the last video, but we haven't done any log applications yet, so we'll tackle that in this video. Okay, so when working with when working algebraically with logs, there are a few log laws that we want to be comfortable with, just like exponent laws. Okay, you know with your exponent laws that when you are multiplying powers of the same base, you add the exponents together. When you're dividing powers of the same base, you subtract the exponents from each other. And when you're taking a power of a power, you would multiply the exponents together. Okay. So the following are some log laws that you want to be familiar with. They are all on your formula sheet. So let's look at this red one first. That is switching from exponential to logarithmic form. Okay, and we were dealing with that in the last video a bit. If you recall, I went through this little mantra that says the base becomes the base. Okay, the dude that was free is now locked into the log, and the dude that was locked as the exponent is now free. And that can go in both directions, okay? Then in the previous one, we also used this guy. This guy is the change of base identity. Log base b of c, we can change that to any base we want by going log base a, which is just means the new base that we're going to use, of c divided by log base a of b. Now where that came into play is like if I had asked you to do log base 2 of 3, what we could do in our calculator, especially for those who don't have that fancy log button, you can just go log 3 divided by log 2. But when we go log 3 divided by log 2, what we're actually doing is using this change of base, and we're changing it to base 10, okay? Okay, then we have log base b of m times n. So when I have factors inside here that are being multiplied by each other, I can expand that to be separate addition of logs. And when I have items that are being divided by one another, I can expand that to be separate subtraction of logs. Okay, and then the final one is a power log law. If I have an exponent on the thing I'm taking the log of, that exponent can come to the front of the log, okay? So it'll be n log base b of m, okay? When you're writing these guys, especially in written response questions, it's really, really important that you show the proper lines, okay? So like for instance, this b needs to be a subscript. It needs to be little and hanging kind of right below the g, whereas the m needs to be in line with the word log so that it's not confused that it's a base, okay? Likewise, the exponent on m has to be a superscript. It has to be up, little, up in the corner of m, okay? So just take your time when you're writing these things. Make sure you're writing very, very carefully so that there's no ambiguity. You don't want your marker to look at that and say, well, do they really know what they're talking about, okay? Not on your formula sheet, but also helpful to know is log base a of a is 1. So the log of anything that is the same as its base will end up being 1. And that's actually pretty simple if you think through the change of base identity, right? This would have become log a divided by log a, and anything divided by itself is just 1, okay? Also helpful to know is log base a of 1 is 0, okay? All right. So when solving exponential and logarithmic equations, we have the following tools available to us, and we're going to take a look at all of them, okay? We could graph the left side in y1 and the right side in y2 and solve for the x value of the point of intersection. And I've walked you through a few of those in other contexts, but it's the same for logs. We could try and make the bases the same. And then once you have the bases the same, you can pull the exponents, okay? So that's specific to solving exponential equations. And then we could also convert to log form from exponential or vice versa to get some sort of variable unlocked. Or we could take the log of both sides, okay? And we'll go through a couple of those momentarily here. Okay, so first of all, rewrite the following in exponential form. Again, this is just to get practice getting good with switching forms. So base becomes the base. So this is going to be 3 to the something. The 7 was free, so he's now the exponent. So it'll be 3 to the 7 equals x. Okay, over here, the base becomes the base. So it'll be base A. This guy was free, so he's now the one locked up. So it'll be a to the b equals 4, or 4 equals a to the b, doesn't really matter. And then the last guy, the base is d. The dude that was free is g, so it'll be d to the g equals f. Okay, d to the g equals f. Okay, now let's try the other way. Rewrite in logarithmic form. Okay, so base becomes the base. Now, though, it's going to be log base 3. Okay, so then it's the 9 that was free, so he'll be locked into the log. So it'll be log base 3 of 9 equals x. Okay. This guy over here, the a is a little problematic. Let's get rid of that a first. We'll divide both sides by a. Then the base becomes the base, so we're looking at log base 4. B over a was free, so now it's going to be locked into the log. So it'll be log base 4 b over a equals x. Okay, and then the last guy, base becomes the base, so it'll be log base b. A was the free guy, so he'll be locked into the log. So it'll be log base b of a equals 4. Okay. All right. Okay, here we go. Use log laws to simplify each statement down to one term. Okay, so what I want you to see in this first one is I'm subtracting logs of the same base. When I subtract logs of the same base, I can divide the things I'm taking the log of. So I can smush this together to be one log by saying it's log base 7 of 8 over 4. And then 8 over 4 is just 2. So log base 7 of 2. Okay, the next guy, same thing, I'm subtracting. So it'll be log base 3 of 32 over 8. And 32 over 8 is 4. So log base 3 of 4. And then this last guy, I'm adding this time, so I can smush those together by multiplying the things I'm taking the log of. So that'll be log base 5 of 14. 2 times 7 is 14. Okay? Awesome. Okay. Now, again, we're still looking at trying to get these to one term. The number in front is a little problematic. So what we want to do is we want to use the power log law, bring that up as an exponent first, and bring that up as an exponent. Okay, so this is going to be log base 4 of 3 squared, which is 9, and log base 4 of 2 cubed, which is 8. Okay, once I've done that, now I can look at the fact that I'm adding logs of the same base together. So I can multiply the 9 and 8 together to smush this together to be one log, and that'll be log base 4 of 72. Okay, all right, over here then. I've got, let's bring that 2 up first. Okay, so that's going to be 4 squared. So that'd be 16. And so I'm going to end up with 3 times 16 and divide by 12. Okay, anytime we're adding the logs together, we would multiply. And anytime we subtract a log, that ends up as a division. So it ends up on the bottom of a fraction. Okay, so that ends up being, so the first thing I did there was just get rid of the 2, brought it up as an exponent. And then 3 times 16 is 48, and then 48 divided by 12 is 4. Okay. Okay, the guy on the bottom, again, I want to bring that 2 up to the exponent first as an exponent on the 5. So that'll be log base 2 of 25, 5 squared. Then I've got 15 divided by 3. So I did that in one step here. I just looked at this and said, okay, log base 2 log base 2 of 15 minus log base 2 of 3 is the same as saying log base 2 of 15 over 3. 15 over 3 is 5. So I did that here, and I brought that 2 up as an exponent, and that's what made that be the 25. Okay, now I'm adding these logs together. I can smush them together by multiplying the 5 and the 25. Okay, and so 5 times 25 is 125. So I'm left with log base 2 of 125. Okay, just trying to get comfortable with the log laws. Okay, which of the following equations is equivalent to 4 to the x plus 2 equals 16? Now, let's play a little bit of the multiple choice game here for a sec. Look at your answers. They all involve logs. So really, this is just a fancy question to say, convert this to log form. Okay, well, base becomes the base. Okay, so I'm looking at log base 4. Well, automatically that rules out A and B because those are not log base 4. Okay, just understanding that the base has to become the base is the 50-50 card here. And now we're looking at C and D. Now, the dude that's by himself would be the dude locked. So 16 needs to be locked. And the x plus 2 was locked. So now he needs to be free. So that points to the answer of D. Okay. Good. Okay, when the expression log base 8 of 6 plus log base 8 of 4 is simplified to form log base 8 of A, the value of A is, well, I'm adding two logs together. When I add two logs together, I can simplify it to a single log just by multiplying the 6 and the 4 together. So 6 times 4 is 24. Okay. They're just testing to know that you understand how to apply those log laws. Okay, when log base b of 3x plus log base b of 5 to the x minus log base b of 6x squared is expressed as a single logarithm, the result is. Now this one's a little bit more in depth. There's a few more layers to it. That's okay, we can handle it. First of all, let's deal with these first two. I'm adding separate logs together, so that means I would multiply the 3x and the x to the 5. Okay, so 3x times x to the 5 would give me 3x to the 6. Then I'm subtracting log base b of 6x squared, which means I will want to divide that. Okay, so now 3x to the 6 divided by 6x squared. Well, 3 over 6 is going to give me a half. And x to the 6 divided by x to the 2 would give me x to the 4 on top. So I'm going to end up with x to the 4 on top and a 2 on the bottom. And that sounds like C to me. Okay. Okay. To graphically determine the solution to the equation 3 times 5 to the x equals 2, each of the 4 students entered different functions in their calculator as described below. Now, when I get a big, long question like this, I skip all the students and go right down to the question. I want to know what they want me to figure out about these students. The 3 students who began a process that could lead to the correct solution. Okay, so I know 3 of them are right and 1 of them are wrong. Okay, so let's read what each one did and see if we can determine who is wrong. Student 1, she entered the function y1 is 3 times 5 to the x minus 2 and found the 0. So essentially, she said, hey, I'm going to take this 2, I'm going to bring it over to that side. So I'm going to subtract 2 from both sides. That would end up with 0 on one side. So she found the zeros. I think that's a perfect thing to do. Student 1 sounds awesome. When I grow up, I want to be just like student 1. Student 2, she entered the 2 functions. y1 equals 5 to the x and y2 equals 2 over 3. So what did she do? It looks like she divided both sides by 3. Is that valid? Sure is. Then she went and found the intersection point of the 2 graphs. I think student 2 is also pretty awesome. Student 3, he entered the 2 functions y1 equals x log base 10 of 15 and y2 equals 2 and found the intersection point of the 2 graphs. So if we look up at, I'm going to actually take my picture off there just to make sure you can see that. X log base 10 of 15. Well, this is where he was. There's no way to have done that, x log base 10 of 15. He multiplied the 3 and the 5 together first, and that's a critical error, right? Because that exponent only applies to the 5. It doesn't apply to the 3. So student 3 is totally wrong. Don't be student 3. Now, let's just make sure, though, that student 4 is okay. He entered the function y1 is log base 10 of 3 plus x log base 10 of 5 minus log base 10 of 2. That is actually correct. I don't know if many of us would have done that right off the bat, but essentially what he did, I'm going to write this one on the board here for a second. He took the log of both sides. So he went log of 3, 5 to the x times 5 to the x equals log of 2. And then he said, okay, I'm multiplying these together, so I'll expand that out to be separate logs. And then he said, okay, the x can come to the front, and I'm going to subtract log base 2 from each side. So even if it's not something you would have thought of, it's not illegal. It's a valid way of solving. So student 1 and student 2 and student 4 are all correct. Okay, 1, 2, and 4. Okay, the value of x in the equation 729 to the x minus 1 equals 9 to the 2x minus 1. Now, we talked about a bunch of different strategies on how to solve this. I think the easiest thing to do is to write these as the same base. 9, I can write 729 as 9 to the 3. Okay, so I could change this to 9 to the 3 to the x minus 1 equals 9 to the 2x minus 1. Okay, then I have a power of a power right here, so I'm going to multiply the 3 into both of those terms. Very common mistake that kids don't multiply the 3 by the negative 1, so just be careful of that. So that'll end up being 9 to the 3x minus 3 equals 9 to the 2x minus 1, and then what I've done is I just pulled the exponents out. Once you have them as a single power that has the same base, then the exponents have to equal each other, so you can just pull the exponents out. So 3x minus 3 has to equal 2x minus 1, and then I can subtract 2x from both sides and add 3 to both sides. X has to give me 2. Okay? Good job. All right. Which of the following graphs could be used to determine the solution to the equation 3 equals 2 times 5 to the x? Okay, so if I was going to put this in y1 and put this in y2, I would have a horizontal line at 3. So let's just look. 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1, 2. Okay, so just that thought there rules out A and C because they have a horizontal line at 2. Okay, then in the next guy, I know I need to grow, but that's not super helpful because they all grow. I know my y-intercept has to be 2. Okay, so in B, my y-intercept looks like 2, but in in D, my y-intercept looks like 1. So B is correct, D is wrong. The answer would have to be B. Okay. Okay, which of the following equations could be used to algebraically solve the exponential equation? Well, again, I just want to make the bases the same. So my 9, I can change to 3 to the 2. Okay, if I do that, this will be 3 to the 2 to the x minus 3. So that 2 will apply to the x and apply to the negative 3. So that's going to become 2x minus 6, making them both be 3. And so my answer is B. Okay, an expression that is equivalent to 3 log A minus 3 log B. Okay, well, I probably want to get rid of this 3 in front, so let's bring that up to the exponent, first of all. Okay, so that's going to give me log A cubed minus log B cubed. Now, when I'm subtracting logs, I just divide. So that becomes log of a cubed divided by b cubed. Okay, but a cubed divided by b cubed is the same as saying a over b all to the 3 because they're both cubed. Okay, so that would make my answer D. Okay, given log base b of c equals a and b can't be 0, which of the following statements must be true? So you're told that b can't equal 1. But you also, now, I mean, you could just start plugging things in. Okay, you could, it says b, a, answer A says b has to be greater than 0 and a has to be greater than 0. So pick a value for b being equal greater than 0, like b could be 2 and a could be 3, and see if that works, see if you can solve it. Okay. The answer to this, though, is actually B. And the reason we know that it's B is because your base can't be negative here, and you can't take the log of a negative number. Okay. Now, if you were going to guess and check your way through, though, you would still arrive at the same answer. Okay. The other ones don't have to be true, but that answer B there must be true. Okay. Okay. Solve the following graphically. Answer to 3 decimal places where necessary. So we're just going to stick this in Y1, stick this in Y2. You're going to get me a decent looking picture and then solve the X value at your point of intersection. Picture you should have gotten looks like this. Okay, and then your answer ended up being 0.539 to 3 decimal places. Just be really careful that you follow the right rounding instructions. Okay. Okay, this guy, again, same thing. 4 to the 5x minus 1 will go into y1. Just a quick word of caution, if you have a white Casio or an older model TI, when you go for exponent, you need to make sure then you open up a set of brackets before you go 5x minus 1, okay? On the newer Casios and on the newer TIs, when you open up that exponent button, there's a little box that appears. If that little box appears, you don't need to worry about the brackets, but if you're writing everything in one line, you do need to make sure you've got the brackets situated properly, okay? Okay, so the picture you should get looks like that. And then the X value there is 1.25. That was exactly 1.25, so I didn't write 1.250, okay? Okay, just a couple of application of log questions now. In 2010, or the 2010 earthquake in Haiti measured 7.0 on the Richter scale. In 2004, an earthquake off Indonesia measuring 9.1 on the same scale caused a tsunami. In order to compare relative intensities, I, of the two earthquakes, the following formula may be used. I equals 10 to the m over 10 to the n, where m and n are the Richter scale values of each earthquake. Okay, compared to the earthquake in Haiti, the earthquake off Indonesia to the nearest whole number was blank times stronger. Well, anytime you're trying to figure out I'm this much times stronger, let's say I am 3 times as old as you. Well, if I'm 60, how old are you? You're 20. Well, how did you do that? Because 60 divided by 20 gives me my 3. Anytime you're looking for that intensity ratio, you're going to take the big guy, or the higher number, or the stronger guy, or the more intense guy, and you're going to divide by the weaker number, or the smaller number, or the least intense guy. So the more intense, oh, sorry, I don't know why that flicked back on you. The more intense one here was the 9.1, and the weaker one was the 7.0. So we're going to go 10 to the 9.1 divided by 10 to the 7.0. Now, that equals 10 to the 2.1 if you remember your exponent laws, but even if you don't, you can just type that in your calculator. But when dividing powers of the same base, you can subtract the exponent. So 9.1 minus 7.0 is 2.1, and 10 to the 2.1 is 126 when rounded. Okay, so the earthquake off Indonesia was 126 times stronger than the earthquake in Haiti. Okay. All right, and then from 1997 to 2008, the population of a particular town grew at an average rate of 5.4% per annum. During this 11-year period, its population P can be modeled by this function, where X is the population in 1997, R is the average annual growth rate. Now take note, the way they set this up, it's 1 plus R. We talked about this in the previous video around getting the rate. They already added the 1 for you there. Okay, and N is the number of years since 1997, which they also were fairly kind to you and said, hey, that's an 11-year period. Wasn't that nice of them? Okay, in 2008, the population was 14,030. So that's the final population, not the initial population. According to the model, the population of this town in 1997. So you're actually asked to get the initial population, okay? But they've given you P, they've given you R, and they've given you N. So you're just gonna plug all those numbers in, okay? Whoops. So P is 14,030. R was 0.054. Remember that your rate always has to be a decimal, not a percentage there. And then N was 11 years, okay? So this guy is just a number, whatever that number is, it's being multiplied by X, right? So we just need to divide both sides by that number. So X is going to equal 14,030 divided by 1 plus 0.054 to the 11. Now, if you have a newer TI or a gray or black Casio, open up that fraction button first and you don't have to worry about any brackets. If you don't, if you have a white Casio or an older TI, you're going to want to go 14,030 and then divide and then open up that bracket, type that in, close, and exponent 11, and that should get you there. Okay, and that should get you an answer of 7,867. Okay, next up. The pH of a solution, P of X, is defined by the equation P of X equals negative log X, where the concentration of hydrogen ions, X, in a solution is measured in moles per liter. Calculate the pH of a solution with a hydrogen ion concentration of 6.5 times 10 to the negative 6. Okay, so just like every other question that you're being asked, you ask yourself, is this 6.5 times 10 to the negative 6, is that an X value or is it a P of X value? And in this case, it's an X value. So you are going to plug that in for X, and then you just type that in your calculator. Now, as far as the times 10 to the negative 6 goes, you can physically write times 10 exponent negative 6. Your calculator also has a times 10 to the whatever button. On a TI, it's called EE, it's capital E, and you'll find it as the second function of your comma. On a Casio, you'll either see it as an EXP button, or in the newer models, it now says times 10 to the X button. And you'll find that just to the right of your negatives, or sorry, to the left of your negative sign, okay? Type it in and you should get 5.2, okay? All right, that is it for exponents and logs. I'm hoping this feels good for you. And then you have some time to do the extra practice, and I will catch you for set theory. Okay, take care.